Now then, what is nuclear energy? So basically whenever we talk of nuclear energy, we are actually talking of this binding energy per nucleon. So the curve that we have already seen, that it has a long flat middle line. For the lighter nuclei region and for the heavier nuclei region, the binding energy per nucleon is less than 8 mega electron volt, and it is quite constant for the middle ranges. So the greater is the binding energy, the less is the total mass of the bound system, such as a nucleus. So consequently, if a nucleus with less total binding energy transforms into two nuclei with greater binding energy, there will be a net energy release. And this net energy release, as we are seeing that it is of two types, is the main nuclear energy that we are talking about. So if you look at this, why do we talk of nuclear energy? Why is nuclear energy so important for us? Because if you look at this point, the fission of 1 kg of uranium generates approximately 10 to the power of 14 joule, as compared to the burning of 1 kg of coal that gives you only 10 to the power of 7 joule. So the difference that you have is very huge, and that's why we want to use nuclear energy as a source of power generation. So the first kind of nuclear energy that we have to speak of is nuclear fission. So what happens in a nuclear fusion? If you look at this particular diagram, we take a nucleus, a heavy nucleus, a radioactive nucleus, and that will be bombarded with a neutron. Now, since this is being bombarded with a neutron, this neutron will stick to this particular element or this particular nucleus. Since there is an addition of a neutron that is happening, this will increase the mass number. So here the mass number was 235. Now the mass number has become 236. And now if you see, there will be a split that will happen because the mass number is very heavy. What we are talking about is that mass number, when it goes beyond 170, this is where you will see something like this. So this mass number being 236 would have the capacity to undergo fission. So this fission that will happen, it will split into two elements, krypton and barium. So now if you look at this, these two have mass numbers of 92 and 141, which is in the middle range between 30 and 170. So these would be much more stable. So apart from this, there will be a huge amount of energy that will be produced, plus there will be 3 neutrons that will be produced. So in this reaction, you produce a large amount of energy and you produce extra neutrons. Now what happens in a nuclear reactor is that the nuclear reactor will use these extra neutrons for further reactions. So something which is known as chain reaction. Something which is known as a chain reaction. All the neutrons that you are getting from this reaction, this will be further used to bombard more such uranium nucleus. And once you start doing that, this is when you are doing a chain reaction. So a nuclear reactor will have to take care of many things here. We'll just discuss it once we come to the nuclear reactor part. But just understand what is nuclear fission. So if you look at nuclear fission, it is the process whereby an atomic nucleus breaks up into 2 or more major fragments with the emission of 2 or 3 neutrons. This is accompanied by the release of energy in form of gamma radiation and kinetic energy of the emitted particles. Fission occurs spontaneously in the nucleus of uranium-235, the main fuel that is used for nuclear reactors. However, the process can also be induced by bombarding the nuclei with neutrons, because a nucleus that has absorbed a neutron becomes unstable and splits. So the main reason why we would introduce or bombard this uranium-235 with an additional neutron, the main factor behind is that this is more susceptible now to breaking into two constituents and releasing a huge amount of energy. Now what happens is, see, you have two kinds of energies. You have one binding energy, which is very strong force or very strong energy. Then you see something which is a natural radioactivity. Now the natural radioactivity actually does not release a huge amount of energy. Natural radioactivity is happening for all the nuclei which are very heavy, all the radioactive elements, that is the elements that have atomic number more than 83. For all of them, natural radioactivity keeps happening, but this is not a very strong energy. That's why the force that is associated with it is a very weak force, and something which is known as weak nuclear force. But when you talk of this binding energy which is very, very high, the force that is associated with this kind of energy is also very high, and that's why this is called as strong nuclear force. We are talking of uranium-235 here. So now uranium-235, when you talk of the natural uranium is present as a mixture of uranium-238 and uranium-235. The problem is that out of this natural uranium, see, any element that you extract from inside the earth, you would not have a pure element. Even when you talk of carbon is present as carbon-12 plus carbon-14. So any element which it would have, it's all its isotope associated with it. So same is the case with natural uranium also, that you have uranium-238 and uranium-235 present in the uranium. Now the problem is this uranium is 99.3% and this uranium is only 0.7%. The nuclear fuel for us is this. Uranium-235 is the nuclear fuel that we are using. We talk about it, it basically is when, now what happens is, since this is very low, I mean this percentage of uranium is very low, and this is what you have to use as a fuel. Uranium-235 has to be used as a fuel. This naturally cannot be used as a fuel. So that's why this kind of uranium is also called as fissile uranium, because it can undergo fission. So that's why it is called as fissile. Now the problem is it is present in only 0.7% out of the entire uranium that you have. So what we do is we enrich this uranium. You might have heard this term, that is enriched uranium. So now enriching the uranium means that we increase this percentage to approximately 3 to 5% now. And now we are using it as a nuclear fuel. So for nuclear fission to happen, what basically happens is the atomic nucleus breaks into two or more major fragments with the emission of two or more neutrons, accompanied by release of energy in form of gamma radiation and kinetic energy of the emitted particles. And something like this happens in the reaction chain. Now one more concept that you need to know about is critical mass. Now when we talk about critical mass, basically what happens is, if you look at this line, that the fission neutrons, they split other uranium-235 nuclei and a chain reaction is set up. So in practice what happens is some fission neutrons are lost by skipping from the surface of uranium before this happens. So out of these three, some of it may start to skip. Now the ratio of those escaping to those causing the fission decreases as the mass of uranium-235 increases. This has to be exceed certain limit, which is called as critical mass. So that's why what happens is you need a certain minimum amount of mass of this fissile material to be present in the reactor for the chain reaction to be caused. So this minimum mass that you need for the fissile material that can undergo continuous chain reaction is called as critical mass of the material. So above the critical mass, what happens is the reaction may accelerate into a nuclear explosion if uncontrolled. So what I mean here is that the critical mass remains to be exactly what we want it to be. So there is a factor which is called as K. So this factor of K remains or has to be 1. Neither it can be 0.99 nor it can be 1.01 also. Because let's say even if it is 1.01, what happens is, I'll not go into the mathematical details of it, but what happens is the rate of reaction can increase by 22,000 times. So if K is equal to 1, you have a controlled reaction and you can generate power from here. But even if this becomes 0.01, it increases by 0.01 also and becomes 1.01. This becomes an uncontrolled reaction, and this is where the formation of an atom bomb can happen. So such important this particular critical mass has. And you would hear about something called as criticality. That for a given nuclear reactor, it needs to attain criticality before it can start producing power. It can start generating power. So our nuclear reactors, one of it, they just attained criticality. So if they attained criticality, it means that the mass that is there is critical, or just the right amount of mass that you need for the entire chain reaction to happen in a controlled manner is called as critical mass. It can neither be less than that, because if it is less than that, the reaction will stop very, very soon. And if it is more than that, it has a very high probability of being uncontrolled. So neither you can go to a higher mass nor you can go to a lower mass. You have to maintain that right amount of mass for the reaction to happen. So this is something which is called as critical mass. So now what happens is uranium-238 isotope would make an ideal nuclear reactor fuel because it is an absorbent in nature. But uranium-238 nucleus usually absorbs free neutrons without undergoing fission. So this is the demerit that you have with uranium-238. So the unabsorbed neutrons simply become a part of the nucleus. The isotope of uranium-235 is the only natural material that nuclear reactors can use to produce the chain reactions. So that's why uranium is such an important element, such an important mineral. So uranium with an abundant amount of uranium-235 is called as enriched uranium, something that we already saw. So abundant amount means that the presence there is 3 to 5% instead of this being 0.7%. So these are the basics of nuclear fission. Now the next important fact that you need to know is about nuclear fusion. So what we have been discussing until now is for the heavier elements. Elements like uranium, plutonium, these are the ones which are radioactive, these are the ones which are very high in mass number. Now the nuclear fusion happens on very, very small atoms, very, very light nuclear materials, very, very light nucleus. So if you look at this, nuclear fusion happens when two lightweight nuclear fuels are combined and form a nucleus of an heavy element. So if you look at this reaction, deuterium and tritium, nothing but isotopes of hydrogen. So they combine, they undergo fission and they produce helium, and a neutron is emitted with very large amount of energy that is generated. So the products of fusion weigh less than the combined weights of the original nuclei. Therefore the loss of matter, or you can say the loss of mass, has been changed into energy. So that's why now what happens is, let's go back to the discussion that we did for mass defect and binding energy, that from the individual protons and neutrons, when you look at a given nucleus, what you see is that the mass of the entire nucleus is lesser than the constituent masses of neutrons and protons. So the same thing can be applied here also, that these lighter elements, these lighter nuclei, when they fuse together, if the mass of this helium was same as, you can say, if this was the case, that deuterium plus tritium, the mass is equal to the mass of helium, in that case there would be no energy that would be generated. But since that's not the case, it means that there is some amount of energy apart from the mass of helium that is being produced, which will be produced in the reaction. And that's why this high amount of energy is being produced as nuclear energy from nuclear fusion. So the fusion reactions that produce large amount of energy can be created only by means of extremely intense heat. Such reactions are called thermonuclear reactions, and thermonuclear reactions produce the energy of both the sun as well as the hydrogen bomb. So if you look at this reaction, two lighter hydrogen are combining to form a deuterium with emission of beta rays and emission of a neutrino. Then this that has been formed, this deuterium is being used again, or is reacted again with the normal hydrogen to form a form of helium with gamma rays. And this helium will combine to form a better variant of helium, that is more stable helium, and two hydrogen elements. So the net reaction that we are talking of is that 4 hydrogen nucleus is coming together to form one helium nuclei with 2 beta emissions happening, 2 gamma emissions happening, and 2 neutrinos being coming out. So this is what happens in the sun. Now this energy that is generated, that is associated with the gamma rays, this is a very high amount of energy, this energy generation that happens due to nuclear fusion. So now with respect to nuclear fusion, the problem is that when you consider nuclear fission and fusion, what you might have seen is that most of the reactors that we have, all these reactors are using nuclear fission reaction and are not using nuclear fusion reaction. The main reason being that nuclear fusion needs a very high temperature and very high pressures. So just imagine the sun. The temperature inside the core of the sun is in millions of degrees Celsius. So you need to attain millions of degrees Celsius for fusion reaction to happen. Let's consider that we attain it. We are able to attain this temperature. But you also have to maintain this temperature. And this is something which is called as confinement. That you don't only have to attain these temperatures and pressures, you also have to maintain it. And this maintenance is something which is very, very difficult to achieve. And that's why you do not see any nuclear fusion reactors anywhere in the world. Whatever is happening at experimental level. So for a fusion reaction to occur, it is necessary to bring 2 nuclei so close that the nuclear forces between them become active and make them stick together. That is, they have to overcome the Coulomb force. That is the atomic force. That is the, you can say, the electromagnetic force. So the research in fusion aims in confining the fusion ions at very high enough temperatures and pressures for a long enough time to fuse. And to do this, we have 2 different kinds of confinement approaches. One of it is called as magnetic confinement approach and the other one is called as inertial confinement approach. So what happens in magnetic confinement approach is that it uses strong magnetic fields to confine the plasma which atoms to create the conditions needed for fusion reaction production by using the electrical conductivity of the plasma to contain it with the magnetic field. So something very similar to what happens in the sun. The strong magnetism of the sun is something that is able to confine the plasma inside the core so that the nuclear or the thermonuclear reactions or thermonuclear fusion reactions can happen inside the sun. The other method that we can use is the use of powerful laser or ion beams to compress a pellet of fusion fuel to the right temperatures and pressures. Large amounts of clean energy with 0 carbon emission could be produced from such sustained fusion reaction. So if you compare fusion reaction with fission reaction, what happens with fusion reaction is that you are using hydrogen and helium, which are very freely available. Just consider the availability of hydrogen and helium as compared to the availability of something like uranium. Uranium is not readily available. It is there in the Earth's crust, but in very small amounts. But if you consider hydrogen or helium, amount of hydrogen presence in the free hydrogen that is present in the atmosphere, just go back to the first unit that we discussed, in space. The free hydrogen that is present in the entire universe is very high compared to any other heavier element that you are talking about. So that's why if we are able to use nuclear fusion reactors in future, it becomes a very great amount of or a very great source of power production for us. But that is not the case for us right now. So one question, if you look at this, what had come in the prelims examination, that India is an important member of International Thermonuclear Experimental Reactor. If this experiment succeeds, what is the immediate advantage for India? Now, International Thermonuclear Experimental Reactor was meant for nuclear fusion. Now just look at these options that they had given. It can use thorium in place of uranium for power generation. Wrong, because thorium and uranium we have to talk about when we talk of fission. It can attain global role in satellite navigation, of course wrong. It can drastically improve the efficiency of its fission reactors in power generation, of course wrong, because it is related to fusion. It can build fusion reactors for power generation. So such an easy question that was asked by UPSC in 2016. So even if somebody knew even one line about what International Thermonuclear Experimental Reactor is, you know that this is going to be a fusion reactor. Now